Okay, good morning, everyone. Welcome back. Hope you had a good spring break. Just to let y'all know, I'm expecting a phone call that I'm going to need to answer perhaps. So if that happens, just heads up, I'll probably just stop class real quick and deal with that. So it shouldn't take more than 30 seconds, but I'm going to have to take the call. Otherwise, let's talk about the exam. Let me see here. So we took an exam right before the break. I think I did already send out kind of a summary of the grades. I have not done anything in terms of the grades. It's just right now, everyone, it's just the raw grade. I haven't added any bonus or omitted anything, omitted any problems. I've just kept the grades the way they are. You can see here that we had the blue is exam 1, the orange is exam 2. So we had the same number of A's on exam 1 and 2. But the B's, we dropped from 5 B's to 1. We dropped from 3 C's to 2. We had 1 additional D, and then the number of F's went up. Now, the average on the test was a 71, which is actually not terrible. And our standard deviation was a little higher, meaning the grades were spread out a little bit further. So, but the highest grade was a 98. And, you know, yeah, so that's where we are. I think you can kind of see from the grades here that, you know, we had some students that did really well on exam 1 that didn't do so well on exam 2. See, did we have any go the other way? Let's see. We had a few students go up, which is good. So, yeah, question, yes. Lewis?
Yeah, sorry about that, Professor. So you haven't added the 4 points, or you have?
I have not added any. I'm the 5 points for me working out thing.
Yeah.
That's the final.
Oh, okay, cool.
Final exam. Yeah, it wouldn't matter. I could add it here. I could add it later. It'll be the same because the final is weighted the same, I believe, as this exam was. So it doesn't matter if I do it here or later.
It's all but the first are weighted evenly, right?
That's right. The first one was the smallest weight on it because it didn't cover a lot of information. So
real fast, the numbers on this, they're in line with each other. So like the person who got the 98 is the same on the second one's the same person who got the 85 on the first.
Should be, yes.
Okay, cool.
Yep. Yeah, so you should see both, like you should line up both your grades. You should see yourself here. Any other questions or comments about the exam? Okay, so let's talk about where we're headed. We're getting into chapter 7 now, which is applications of antiderivatives. So we're done with all of the techniques. We're done with the improper integrals. Now we're going to start to see what we can do with this stuff. And then my experience is that students do well on chapter 7 because it's visual. It's more visual than what we've done before. So students usually catch on to it. Not to say that it's completely, you know, like easy, but it's just, I think some students who maybe struggle with exam 2 will do better on exam 3 or chapter 7 stuff. So that's a good thing. So we're gonna start with 7.1, talk about areas between curves, and then next class is going to be really important. We're going to talk about volumes. So that's it. We'll get down to business. All right. We have a couple of preliminary ideas that we need to get out of the way. So when we've been in college algebra class, pre-cal, Cal 1, most of the functions that we've dealt with have been functions of the form y equals f of x. So for example, something like y equals 3x minus 4, right? this right here, that's a line, right? And we could replace the y with f of x, and then that's just a different notation. We would say here that y is a function of x. And what that means by saying y is a function of x is that if somebody were to give you x, right? Given x, we can find y. Right? So like if I told you, hey, plug in 2 for x, you would just go, okay, 3 times 2 is 6, subtract 4, you get 2. So now I know what y is, right? Y is 2. So whenever you can solve an equation, this is the important thing. Whenever you can take an equation and solve for this variable, solve for one of the variables, in this case y, then we will say that y is a function of the other variable, which would be x. Y depends on x, right? That's basically what you've done in college algebra, pre-cal, cal 1. It's always been try to get y equal to some equation that has x in it, right? The other side has x. That's not the only thing we can have, though. We could do something a little different. We could take that same equation, y equals 3x minus 4, and instead of looking at y as a function of x, we can try and look at it as x being a function of y, meaning we can solve this equation for x. So let me do that. Let me just add 4 to both sides. And then let me divide both sides by 3. And now I've solved for x, meaning if you give me the y value, I can then very easily generate what the x value is. So we would say here, x is a function of y. Okay, given a y, it will be very easy for us. We can find the x value very easily, right? So those are 2 different concepts. And so what we do is we use a slightly different notation. Up here, we have x equals some function of y. Notice how I wrote g of y. That's letting you know that the x value is a function of y. Where here, we're saying y is some function of x. Those are 2 totally different concepts, all right? Let me show you another illustration of this. Let's say we start with this. Y is equal to x squared. Could you then look at that as y being a function of x? What do you think? Is y a function of x here? In other words, if I give you x, can you very easily give me y?
Yeah.
Yes, right? So we could say here, you know, y is a function of x. Because if somebody gives us y, gives us x, given x, we can find y, right? But let's now try and take this equation and solve it for x. So if we take that same equation and we solve for x, we would have to take the square root on both sides, wouldn't we? And when we take the square root, when we actually come in and initiate a square root, we have to do plus or minus anytime we initiate the square root. So we would have to go plus or minus y equals x. And let me just rewrite it with the x on the left side. Move that to the other side. Now, can you say here that x is a function of y? Can you? Is x a function of y? Is the question. So what I'm asking you is that if you're given the y value, can you easily find the x value?
I would say no, because you'll end up with more than one x value.
That's correct. If I give you y, you're not going to be able to give me a specific x. You're gonna give me 2 values. And that's a problem because that's not the way functions behave. Remember, functions look like this. When you talk about a function, we always like to use a picture. A function, f is what we normally call it, takes some input and it takes that input to exactly one output, right? One input should go to one output. That's what makes a function a function. One thing goes in, one thing comes out for that input. Here, if I give you a y, right? Like let's say I gave you 4, right? Y is 4. Then what are you going to tell me about x? Well, x can be 2 or x can be -2. So now you have one input and two outputs. So you could not say this. No, you cannot say here that x is a function of y. You can say from this equation, yes, y is a function of x, but x here cannot be a function of y. Does that make sense? Algebraically, does that make sense? One input. Over here, we have one input, two outputs. Over here, one input, one output. Plug in 4, you get 16. Plug in -4, you get 16. Still, each input goes to one place. Doesn't matter if they go to the same place, that doesn't matter. It's just that one input, one output. So maybe we can see what's going on with this if we look at it visually. If I ask you to look at y equals x squared and you look at that function, right? If you're in college algebra and I asked you, is this a function, what would you do? What would you do?
Do the vertical line test.
Yeah, you do the vertical line test, right? You do this vertical line test and make sure you don't hit more than once, right? The vertical line test is a test to see whether or not we have a function, right? But what may not have been stressed to you in college algebra, and what I'm stressing to you right now, is that the vertical line test is a test. It does test whether or not you have a function, but it tests if y is a function of x. That's what it's testing. It's saying, if I give you an x, can you easily give me the y? That's what the vertical line test does. It does not test it the other way around. It's not testing to see if x is a function of y. So what makes this not be a function of y is if we draw a horizontal line, we fail the horizontal line test, right? The horizontal line test right? That tests if x is a function of y. So going back, just look at this. Look at this parabola. Is that a function of x? Yes, passes the vertical line test. Is it a function of y? No, it fails the horizontal line test. Understand? Let's look at something different. X equals y squared. College algebra. This is a parabola that opens sideways, like this. Is that a function of x? Is y a function of x here? No. It fails the vertical line test, right? Fails, hits more than once. So this is not, y is not a function of x. Now, is x a function of y? Is x a function of y? Yes.
Yes.
It passes the horizontal line test. So what we could say here is, yes, this, we could look at this as some function of y. G of y equals y squared. We can do that, okay? But what we can never do is look at it as a function of x, because it fails the vertical line test. Back up to this one. This is saying, yes, we could replace the y with f of x equals x squared, we're good to go. But what we can never do is write it as a function of y, because it fails that horizontal line test. So what about that first example I gave you then? This one right here, y equals 3x minus 4. when it solved for y, I had y as a function of x. And when I solved for x, I had x as a function of y. This particular example looks like it works both ways. Well, you can see by the graph why, right? If we graph this, it's a line. It hits at -4. That's your y-intercept. Has a slope of 3, up 1, 2, 3, over to the right 1, and it's a line. So that would pass both the vertical line test and the horizontal line test, right? So you could look at this in both, from both perspectives. You could write this as a function of x, or if you wanted to, you could write it as a function of y. And that was, what was it? It was y plus 4/3 when we solve for x. Both of these are valid, all right? Now, why is this important? Because of what we're about to do, okay? Right now, we're about to look at trying to find the areas between two functions. Sometimes those functions are functions of x. Sometimes those functions are functions of y. And it just depends on the problem, all right? So I needed you to first understand what's the difference between a function of x versus a function of y. All right, let's see if that's enough for us to get through this. All right, so I'm looking at the notes for 7.1, areas between curves. So we are going to start this first concept here by looking at functions of x. Okay, we are looking at functions of x only right now, right? I'll come back to this picture in a minute. Give me a second. I had a great spring break. Everything was great. And yesterday I started feeling like shit. And I feel better today, but my throat's real scratchy. Let me go get a cough drop real quick. I'll be right back. Just give me a minute. All right, I think I'm ready. Excuse me. All right, here we go. So I'm going to start out by, I'm right now asking you to consider only functions of x. So the things I draw need to pass the vertical line test. So let's say we have two functions. The first one, I'm going to call that function f. Everyone agree that's a function of x? Pass the vertical line test. And then I have some other function here, g. That's also a function of x. Pass the vertical line test. What we're interested in is figuring out the area between these two curves, right? Between them. So think back to how we did areas to begin with, right? Let's say we were just looking at the area under F, right? Just F. We know that if we start at A and go to B, right, we can find this area. We can find that area using the fundamental theorem of calculus, right? We basically just need to be able to find the antiderivative of that function, right? So this would be the integral from A to B of f of x dx. That's what that area would be. Area there would be that. Everyone agree? But remember when I was showing you this notation, that there was something really important about this notation I wanted you to understand, that the f of x represented something and the d of x, dx represented something visually. Remember, we did this with rectangles, the Riemann sums. And so we said if we had some arbitrary rectangle in here, the width of that rectangle was dx, and the height of the rectangle was the function's value, right? And so the area of that one little sliver is the height times width, which are these two multiplied together, right? That's basically width times height right there. And what does the integral symbol really represent? A summation, right? We're adding up all of the rectangles that live within this region from A to B, right? The notation here was, I was trying to get you to make a connection between the notation and what it means visually, right? Give me a bunch of areas, right? Give me a bunch of little areas of each of these and then add them up, right? Add them up. We need to do the exact same thing here. For this on the left side, we need to do the same sort of geometric construction. So what I'm going to do is this. Move this down. I want you to imagine that I came in here with a rectangle. Some arbitrary rectangle in here. And I was going to do a Riemann sum. And I wanted to know what the area of that one little rectangle is, right? Well, I can still say that the width of this, let me do this over on this side. I can still call the width of that dx, right? That's how wide it's going to be. It's a little infinitesimal width. The question is, how tall is it, right? So how tall is that? So what I like to do is on the side over here, I like to kind of draw the x-axis. I like to draw just the rectangle. Okay, so what I'm doing is I'm just taking little pieces of this picture on the left and drawing only certain parts of it on the right-hand side. I'm going to label on the bottom of the rectangle the part of the green curve. That's that G curve, right? The G is down there. And on the top is that blue curve that comes through like that. That's our F function up there. And so I would like to know how big this is, how tall this is right here. But that should just be this height, which I know is the function F. That's how tall F is. And then this right here, from here to here, that's how tall the G function is. And so the question mark should just be the difference between those two, right? Should be the F function, take away the G function, and that should give you that black piece. This black piece should be the F function, take away the G function. That should be the case as long as the F function is on top and the G function is on the bottom. Do you agree with that? Which is happening, if you look at the picture, between these two black intersection points right here, between those 2 points, the F function's on top and the G function's on the bottom, right? So this formula should work so long as I'm between these 2 points. Now, let's call these points something. Why don't we call this A? Let's call that B. So this area that I'm looking for here should be equal to the integral from A to B of the sum of all of those little rectangles, which should be the formula f of x minus g of x. That's how tall each piece is, right? Each piece in here, that's the height of each rectangle, times the width, but the width is dx, right? And that should be it. That should work for any two curves that are functions of x, where f is the top function and g is the bottom function. So another way I like my students to think about this is this way. This should be, the formula we should be looking at is something like this: integral from a to b, and it should always be your top function minus your bottom function dx. So long as, again, you're looking at two functions of x, right? Two functions of x, where you have one function above the other one. You have a top one and a bottom one. You'll always just take the top one, subtract the bottom one, and then do your integral. So let's just do an example, all right? Let's do this one. I want us to find the area bounded by f of x equals x and g of x equals x squared. Now, in chapter 7, what's going to really help you is your kind of basic knowledge of what graphs of the basic functions look like. The more you know about the way graphs look without having to reference things, the better off things are going to be for you. But if you don't know what basic graphs look like, you're gonna run into some issues. Probably need your graphing calculator. So just have it handy in case. I would hope that everyone here is comfortable with those two functions. So let me just draw a picture first of what we've got. Let's do the f function in red. So f of x equals x is just the diagonal line. Oops, kind of missed the origin there. That's f of x equals x. And let's do the g function in blue. That's a parabola. It goes like this, goes like that. Not the best parabola in the world, but that is g of x equals x squared. And does everyone see the region that we're talking about that we want the area of? It's the area bounded by the two functions, which should be this region right in here. We want the area of that. With me? So here's what I'm going to do. I'm going to start off. Now, look, what I'm about to do right now is something that you may feel like, okay, I don't really need to do that. You know, he's doing it, but I don't really need to do that. My answer to that would be, yeah, maybe now, but in the next two sections, you're going to need to be comfortable in drawing these things. So get used to this, because we're going to need it definitely down the road. All right, in the next week. So here's my approach. I want that area. These are both functions of x. So I'm going to draw a little generic little rectangle in here. Okay, there's my little generic rectangle. And what I'm going to do is trying to find a formula for the area of that one little piece. And I'm going to do that over here on the side. I'm going to draw my rectangle. Here's my x-axis. Let's see, the red function is the one on top. The blue function is the one on the bottom. And so I know that the height of that rectangle should be the red one, which is x, wait a minute, hold on a second. What? No one said anything. I wrote x squared there. Why did I write x squared there?
I didn't want to say anything because like you were on a roll. Like I was
no,
like,
I'm sorry, that should be x. I apologize. Speak up next time. Sorry. Sorry, my red function is x, the blue one is x squared. So this should be the top function, which is x. Take away the bottom function, which is the x squared function. That clear? That's how tall that little piece is. And of course, the width of this is dx. And so what I want to do is I want to add up all those rectangles, right? I want to add them all up. So I'm going to bring in the integral. I'm going to add up all of those rectangles, all the areas of those, which is, you know, width times height. But I need to know where I need to start and where I need to stop, right? So where does that yellow region start and where does it stop? You can
starts at 0.
Yeah, you can tell by just looking, right? Maybe starts at 0. And where does it end?
Isn't that
wherever they hit each other, right? So I mean, you may just be able to visually look at it. It happens at 1, right? At 1, they hit each other. But let's say we didn't know how to do that. What would we have to do? We would have to take the two functions, set them equal to one another. All right, so I would have to come over here. I would have to find the intersection of the two functions. The intersection of two functions, I set them equal to one another. And I solve this equation. So be careful here. Do not divide both sides by x. Okay, that's a big no-no. Move everything over to one side. Factor out a GCF on the right. Set each factor equal to 0. And you get your two answers, 0 and 1. Those are our two x values where we have intersection, which is where I get the 0 and the 1 from. Now, if you can do it visually, fine. But like I said, later on, this might not be as easy to do. You might have to actually solve that.
So the one further to the right will always be the one on top.
The one further to the
Yeah,
right.
the point further to the right, that one intercept versus the 0, that will be the one that goes on top on your function.
On the integral?
Yeah, oh yeah, on the integral. Sorry.
Whichever point is to the right on the number line will be
Yes.
the top limit of integration. Yes.
Yes. Gotcha.
Uh-huh. So if that would have been -1, then we would go -1 to 0. All right, and that right there should be a problem that you have no problems doing. Right? So you just first find the antiderivative of these, right? You get 1/2 x squared minus 1/3 x cubed. We want to evaluate that from 0 to 1. First thing you do is you plug in 1. Then subtract from that what you get when you plug in 0. And notice when you plug in 0 here, everything goes away, right? All you have is 0. So you just get 1/2 minus 1/3, which should be 1/6. Common denominator, blah, blah, blah. Okay. So the area bounded by both of these curves is 1/6. That's the exact area. Does that make sense? So there's a couple of things we have to do when we look at these problems. We first need to know what they look like visually, right? So that we can determine which function's on top and which one's on bottom. If these are functions of x, right? If there are functions of x, we need to be able to visually see which one's on top, which one's on bottom. We're going to need to be able to find where they hit each other, where they intersect, right? And then set up the integral and just crank out the answer. So let's look at another one here. So here's, in my notes, here's the, let me make this bigger here. In my formal notes, you can kind of make a little more sense out of this now. I have a top function, right? F of x. I have a bottom function, g of x. I've got where the region starts and where it stops. I kind of draw that rectangle over here. Here's my little width. The area of one of these slices is going to be the difference, the f, take away the g times the width. And then the entire area's region is this. And I told you if you replace f with top and g with bottom, right, then this is just top minus bottom. Right? Let's do this one. Actually, wish I didn't have the picture there. In fact, I'm not going to do the picture. I'm going to do this on a different page without the picture. This is the way the problem would appear to you. Okay, so I wouldn't provide you a graph. So sketch the region bounded by these two curves. So we first need to get a picture going here. We look at these curves, y equals 2 minus x squared. Can we look at this as being a function of x? What do y'all think?
Yes.
Yeah, it's solved for y, right? Y is equal to this. So that is a function of x. How about this one? Y equals, can I look at this as a function of x?
Yes.
Yeah, so I'll call it g of x, all right? Now, right now, I don't know which one's on top and bottom, okay? I'm just calling one of them f and the other one g. I don't want you to always think f is the one on top or g. You know, whichever one turns out to be on top is on top, all right? But let's try and draw this. All right, here we go. My first drawing might just be a rough drawing. Let me do the easier one. The g function, negative x. That's just the negative diagonal. Slope of -1. It's just a line. So this is g of x equals negative x. All right, f. When we look at f, I could look at that as being negative x squared plus 2. That's another way to look at that function. Maybe that helps you. That's a parabola, opens down, and it's been moved up 2. So if I go up 2 and draw a parabola opening down, it's going to look like that, right? And I hope it's clear that this is the region we're talking about. Do y'all understand there could be no other region that I'm referring to here? A region has to be bounded, right? It has to be contained within some perimeter. You can't say it's like this stuff down here because that just continues to open up forever. There's no bounded region there. So we're talking about that.
Yeah, the area in that part down there would just be infinite, wouldn't it?
It would be infinite, exactly. Okay, so now I'm going to draw my picture, okay? I'm going to draw my little picture to the side. I'm going to draw an arbitrary rectangle, doesn't matter where this is. And I'm gonna imagine that over here, right? And I'm going to say, okay, this right here is going to be the top minus the bottom. Which for us, what's the top function?
F of x.
The red one, right? Yeah, the f of x. So that's going to be the negative x squared plus 2. And then I need to subtract from that the bottom function. What's the bottom function?
X.
Negative x, right?
Negative x. Yeah.
Negative x. And then the width of this thing, right? We know the width is always dx. So what I'm getting at is that this area, right? The area of just that little slice is going to be negative x squared plus 2 plus x times how wide it is. Okay, so I'm saying that area in there, right, is equal to how wide it is, dx, times how tall it is, which is the top minus the bottom. Right, that is where that comes from. Any questions there? I need to add them up, which is where I'm going to bring the integral, but I need to know where they hit each other, right? I need to know where these two graphs intersect. On the x-axis, I need those x values. So to get those, I'm going to have to find their intersection, which means I'm going to have to set them equal to one another. So for the intersection, I'm going to have to set negative x squared plus 2 equal to the other function, negative x. And I can tell by looking at this, this is a quadratic, right, equation. So I'm going to move everything. I'm going to move everything to the right side. That way I have a positive x squared. So I move this negative x squared to the right, move this 2 to the right. And I think that factors. Am I going to get lucky? Does this factor? It does, right? X minus 2, x plus 1. So I have two answers, 2 and negative 1. So this question mark, I wasn't sure. Now I know it's negative 1. And this one right here, I know is 2. And that's going to give me my limits on my integration, right? My limits of integration. So here comes the integral. Integral goes from negative 1 to 2. What I'm integrating is negative x squared plus 2 plus x dx. And again, now that you're looking at that, you should be like extremely happy, right? Because that's not the type of integral that we should be concerned about. There's no integration by parts, no trig sub, no partial fractions here, right? This is a pretty clean thing. And it's not an improper integral, right? We don't have infinities anywhere. So we're good to go, right? We just start cranking this out. So this is just going to be first the antiderivative, so negative 1/3 x cubed plus 2x plus 1/2 x squared. Evaluating that, -1 to 2. You plug in 2 first. Okay, subtract from that what you get when you plug in 1, or sorry, -1. All right, so this is gonna suck, but I mean, it's just arithmetic now. So I should get -8/3 here. Cubing the 2 gives me 8, hitting it with a -1/3 gives me -8/3, plus 4. Let's see, 2 squared is 4, half of 4 is 2, so plus 2. Minus, okay, over here, when I cube the -1, I get -1. And then I hit it with a -1/3, that gives me +1/3. Then -2 or -2. And then I square the -1, that gives me 1. So I'm adding a half over here. I am going to distribute that negative through the parentheses on the right. Okay, so I put the 4 and the 2 together to give me 6, and I just distribute that through. Hoping this will make things better. Not really. I can put this, this, and this together, right? That gives me -10/3. And then the 6 plus 2 is 8. And then I'd have to get a common denominator here. Turn 8 into 24/3, and then put those together, I should get 14/3. 14/3.
That's correct.
Thank you. All right. So again, think about the way the problem appears. Sketch the region bounded by these 2 curves. You've got a lot of things you need to, draw out, figure out what's on top, what's on bottom, where do they intersect, right? Does all make sense? All right, take 5 minutes, see how far you can get with this one. I'll go 5 minutes and then I'm going to start working it. This problem is a little different, so be careful. Okay, let's start talking about this. First thing, you need to know what the square root of x looks like, right? So hopefully you're all comfortable with this idea. Square root of x looks like this, roughly speaking there. Okay. And then let's see, the blue function, y equals x minus 2, I'm going to call that g of x. That's just a line. It's got a y-intercept of -2, so down to somewhere down here. And it just looks like a diagonal. It goes like this. Roughly speaking. Right now, we do not have a region bounded by both because this right here is open, right? This just kind of opens up here. So this y equals 0 is actually the x-axis, isn't it? Goes like this. That's y equals 0. And so now you can hopefully see the region we're talking about. It's this right here. Go with me? Now we have an issue. We have an issue because what I'm supposed to do is try and figure out like what a rectangle looks like in there and the top and the bottom, figure out, right? But there's an issue because it depends on where I draw my rectangle. If I draw my rectangle over here, then the top function is the red one and the bottom one is the blue one, right? But if I draw my rectangle over here, it's different. The top is the red and the bottom is the green, right? It's two different things. In the problems we've done before, right? When I drew this rectangle, it really didn't matter where I would have drawn this rectangle. It was arbitrary. The red one's always on top, the green one's or the blue one's always on the bottom. It's always never changes, right? It's always the same thing. Here, it does change, right? So I have to recognize that right here at this point, which I'm actually not quite sure what that point is yet, I have a shift in things. So what I'm going to do is I'm going to break this into two integrals. I'm going to get first the integral that's going to give me the area of this piece. And then I'm going to add to it the area that gives me the area of this piece over here. Does that make sense? Where it transitions from red on top, green on the bottom, where it transitions from that to red on top, blue on the bottom, I'm going to have to break and separate it into two separate pieces. Does that seem reasonable to you? Okay. Well, in that case, I should probably figure out where these points are. I think we can do it. I hope you can do it visually. That's 0, right? That's the first point. How about this one right here? Can you tell where that is?
2.
At 2, right? That's where the blue line hits the x-axis. So if you were to take your g function and set it equal to 0, you get 2. And then how about this point here? How do we get that one?
I solved for it, but it's 4.
Okay, so you set what equal to what?
The root x equal to the x minus 2.
So for that, you set the red function root x equal to the blue function x minus 2, right?
Mm.
Set it because we were trying to figure out where the red and blue hit each other. So we set the red and blue ones equal. And how do we solve this?
I don't think I solved it technically right, but the math works, which is I brought my x over. And once you look at that for just a few seconds, you can see that if you make x forward, you get -2.
So you could do that just by a visual inspection.
Yeah.
Right. You could just be, oh yeah, 4 works, right?
If it was any more complicated, I would have been screwed doing that. But
yeah.
It's a simple enough problem. I was able to just look at it for a few seconds and go.
Okay. So say it wasn't simple. How do we solve that? What type of equation is this? It's not quadratic.
It's
This is a root equation or square root equation.
Yeah.
There's a whole set of steps on how you do this. The first step is to isolate the square root by itself on one side of the equation. So I've got a square root isolated. Once I have it isolated, I square both sides of the equation. And that gives me an x on the left. On the right, I have to expand that, which means I have to multiply it out loud. I'm not showing that work. I'm trusting you can do x minus 2 times x minus 2, FOIL it out, collect like terms. Then bring everything over because it's now quadratic. And
Taking
then
it
hope
way
you can
back.
factor. What's that?
No, you're taking it way back. I forgot how to do that.
You remember seeing that though now? Yeah, maybe. You have to factor this now. If it doesn't factor, you would have to use a quadratic formula. All right, but it factors. And you get 2 solutions. You get 4 and 1. Now, there's something you have to remember about root equations. Whenever you have root equations and you're solving them, you always have to check your answers because there's a possibility that one or both of your answers don't work, or maybe they both do work, but you have to check them. So if I check right now, remember that this was the original equation that I was trying to solve, right? That was it. If I plug 4 in here, 4 works, right? 4 works. But does 1 work? Plug 1 in here, square root of 1 is 1. 1 minus 2 is -1. You get 1 is equal to -1. That's not true. This is an extraneous solution.
Is that because depending on how it's done, the square root will sometimes put a positive and a negative out?
Anytime you square both sides of an equation, you always introduce the possibility of extraneous answers.
Okay.
And it's because of the whole idea that when you square something, you lose the positive negativeness of it, right?
Yeah, that's in case something was a negative effect.
Exactly. And you can see that when I tried plugging in 1, I got 1 equals -1. And see, they were off by a sign. When we squared, we kind of like lose that. That's why you have to check the answer.
Gotcha.
Okay, so we only have one answer 4. Okay, so let's see if we can set this up, see if this all makes sense to you now. I'm going to try and find the area of this whole thing. Okay, so what I'm going to do is this. First, I'm going to look at only the area between 0 and 2. Figure out what that is, and then I'm going to find the area from 2 to 4. Now, when I go from 0 to 2, what's the top function? When I'm in this region, what's the top?
Root x.
Root x, and what's the bottom?
0.
0, right? The 0 function, the green one. So I'm going to write it, even though I don't need it. It's the top function minus the bottom function. That's how tall the rectangle is. and then the width is dx. Now, when I get to the second one, the top one is the square root of x, and the bottom one is the x minus 2. So it'll look like this, square root of x, top one, minus bottom one, be careful, you have to have the bottom one in parentheses, dx. Does everyone see it? Top minus bottom, right? Top minus bottom, right? Subtracting. They both have the same width, dx on each one. The way that I like to think about the rectangle we drew, you know that rectangle I drew in the first one? I just shaded it green. This green rectangle, what's happening is you're adding up all the rectangles between 0 and 2. So that's like taking all the possible rectangles that you could have in here, right, between 0 and 2, and adding them all up. And then on the other integral, you're going from 2 to 4. So you're looking at all the rectangles in here, the red rectangles, right, all of those between 2 and 4, and adding all those up. And when you sum those together, you should get the total area. Got it? Now, this ... I'm not doing that, okay? We don't have time for that. That's easy stuff now. Would you all agree? Hopefully you agree, yeah? I mean, we're not even gonna go through the work on it, all right? So on the next test, there are a few problems I'm gonna ask you to go all the way to the answer, okay? I will ask you to go ahead and get me down to 1/6, whatever it is. I'll probably ask you 1 or 2 of those where you have to grind it all the way to the answer. And then from that point on in the test, I'm only going to ask you to set up the integrals, which means I just want this, and that's it, you're done. Okay? Now that's good and bad. Good, you don't have to do all the tedious work. Bad, I can ask you more questions now, right? Because then I'm just set up. Because at the end of the day, it really is, we would go to a computer for this answer at this point. Like in the real world, like you get the integral set up, you go to the computer to get the answer. But it's the setting it up, right? Like there's no computer program out there yet that you can type this sentence in or type in this and it's going to go give you the answer, right? I'm pretty sure we're not there yet. Are we? I can't take a picture of that with my phone and get the answer, can I?
We could do the graphing on a computer, but not, you know, working out what the integral would be from that.
Yeah, I know that there's certain, you know, apps that you can get on your phone where you could just take a picture of this equation right here and it would solve the equation for you. But I don't think you could take a picture of the question that I started with and it give you the answer. We're just not there yet. So it really is about translating the real world problem into the integral. And then once you get to the integral, then we use the technology to get the answer. Okay, y'all doing all right with this? I'm going to go to a computer to do this real quick because I do want to know the answer. So give me a moment. Hey, what's going on here? So let me try and do this. I'm going to do an integral from 0 to 2, and then it was the square root of x dx, and then I want to add to that the integral from 2 to 4, and then it was the square root of x minus, and then it was x minus 2. It should take that. Ten-thirds is the answer. All right, 10/3.
Really likes those weird top-heavy fractions with these past couple.
All right, now go back to this. Okay, same problem. I'm going to draw the picture again. Okay, and then we had this coming through. And then we had this coming through like this, right? Basically, that's what we had. So look, to do this problem, we had to break it into two integrals, right? Because when we drew our rectangles, in here, we noticed that in this region, we had two different scenarios, right? The top and bottom was different in each one, right? Well, the bottom was different for each of those two, all right? I want us to look at this from a different perspective now. What if instead of me doing that, I did my rectangle horizontally instead? Ooh, that's terrible. In other words, instead of looking at this as functions of X, let's look at them as functions of Y. So can we take this red one and can we solve it for X? Well, we could square both sides and we get this, right? If we square both sides. So now I could call this f of y equals y squared, right? That would be this red one. On the blue one, could I solve this for X? Well, sure, I could just move the 2 to the other side and get y plus 2. And then I could call that some function of y plus 2. So in other words, these both pass the vertical line test, so they are functions of X, but they also both pass the horizontal line test. Do y'all see that? So I could have looked at it from two different perspectives. And when I look at it from this perspective of functions of y instead of functions of X, then I can draw my rectangle sideways. And instead of moving my rectangle instead of having a vertical rectangle that moves left and right, I can have a horizontal rectangle that moves up and down. And so maybe you can help me with this. How wide would that rectangle be? It's not going to be dx anymore because it's not x that's changing left and right, right? What's changing? Up and down?
Dy.
That'd be dy, right? That'd be dy. And then we need to know, well, how wide is this? How wide is this piece? Well, we would have to know, first of all, how wide is it from here to here? That's this edge of the rectangle. Isn't that the blue function? That's the blue function. But it's a blue function of y, not a function of x. So this should be y plus 2. And then I need to know what the inner piece is from here to here, but that's the red function written as a function of y, not as a function of x. So this should be y squared. So what would the black piece be then?
Y plus 2 minus y squared.
It should be the y plus 2 minus the y squared. So instead of top minus bottom, this is really what minus what? Not top minus bottom, but
Right minus left.
right minus left. It would be the function on the right minus the one on the left. How do y'all feel about this? Nod of your head, yes or no? Okay. So what would my integral look like? I know that on the inside, I would have y plus 2, that's the one on the right, minus the one on the left. Okay, so this is the one on the right, minus the one on the left. dy is how wide it is, but what about my limits of integration? Remember, we're moving our rectangle up and down now, right? Not left and right. So it's not going to be my x values. It's instead going to be the y values, right? It would be, okay, what is this? And then over here, isn't it just 0? Y equals 0? We go from 0 to something, right? Where do we go to? 0 to, how would you figure out where you go to?
We could just plug in our answer from the previous one into our y for that point
Sure.
at the end.
Sure, we could, assuming we had done that. Let's imagine we hadn't done that, right? So you would want to know where these two intersect each other, wouldn't you? So you'd set these two equal to one another. You'd set y squared equal to y plus 2, right? Move everything over to one side. And then that factors. And you get two solutions. You get 2 and you get -1. It has to be 2, right? Has to be 2 up here on the y. So that goes from 0 to 2 there. So let me write that down. We've got integral 0 to 2, y plus 2 minus y squared dy. I'm going to work this one out. This is 1/2 y squared plus 2y. I'm taking the antiderivative minus 1/3 y cubed. And I'm evaluating this from 0 to 2. When I plug in 2, I get 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 cubed minus, now when I plug in 0, it kills everything off, so I just get 0 here. This should be, let's see, 2 plus 4 minus 8/3. Or 6 minus 8/3. And if you get a common denominator, you get 18/3 minus 8/3, which is 10/3. Same answer. Should be, right? Better be. But what would you say was easier?
This one.
This one probably, because we didn't have to split it, right? We didn't have to do 2 different integrals. We just had to do 1.
And we also didn't have to solve for 3 different points.
That's right. So the moral of the story is this. When you look at the region, you have to decide for yourself, what would be better? Using vertical rectangles, where you're treating all of your functions as functions of x, or using horizontal rectangles, where you're treating all your functions as functions of y. And that's completely up to you. Sometimes you don't have a choice, but sometimes you do, like in this problem. So if you go back to my notes, this is how we set things up if you have functions of x. If you have functions of y, you're going to be doing this integral from, I'm using c to d. C and d are the 2 y values that represent your kind of the top of where your rectangle goes and the bottom of your rectangle goes. So instead of a and b being left and right endpoints, c and d are kind of like your lower and upper. And then instead of top minus bottom, it's right minus left. Now I don't have it written here as right minus left, but I want you to think about it that way. Okay, let me see here. We did that one. Let's do this one. All right, when I'm looking at this, I'm already thinking right now that I'm going to have to keep this as functions of x. And that's because if I had to solve this right here for x, I would have to bring in an arc sine. And I really don't want to mess with the arc sine function, right? So I think I'm just going to leave everything as functions of x, which makes me think I'm going to probably have vertical rectangles here. Let's see. I'm going to try and draw a picture. So first, I'm going to start with the picture of sine of x.
I have a question. So
Yes.
Does that mean that we have to include absolutely all those 3 inside? Or all
those
4?
Yeah, everything here has to be included. So let's look at We want to sketch the region bounded by sine x. Okay, so sine x looks like this. Goes backwards as well. I know that this hits at 2 pi. I know this is pi. I know it has a peak at pi over 2. I know it has a lower peak here at 3 pi over 2. I know that because I took pre-cal. Okay, y equals x is a diagonal line, right? Ooh. I'm not quite sure if that's drawn right. Not quite sure. X equals pi over 2. X equals pi over 2 is a vertical line at pi over 2. All right, let me label this. This is x equals pi over 2. This one was y equals x. And of course, this one is y equals sine x. And then x equals pi. Let me do that one in green. That's this right here. Do you all see the region bounded by all 4 of those?
Would be that spot.
Right here. Vertical rectangles make sense here. Think about it. No matter where I draw my rectangle, right? No matter where I draw it, I'm always going to have the blue function on top and the red one on the bottom, right? Blue on top, red on bottom. Blue on top, red on bottom. No matter how I draw the rectangle. Yes?
I feel like the X lines are really more of just like a domain restriction than anything.
Yeah, exactly. Like we need to know where to start this and where to stop this, right?
Yeah.
And that corresponds to our pi over 2 and our pi, right? So those two just gave us our limits of integration. So I should be able to, I'm going to go straight to the integral. See if you follow this. This is the integral. I'm going to start at pi over 2. I'm going to end at pi. Then I'm doing top minus bottom. The top one is x minus the bottom one is the sine curve. Dx, that's how wide each rectangle is. That's it. I'll go one more step, but I won't go any further. The antiderivative of that's 1/2 x squared minus cosine x plus cosine x, sorry. Right, the antiderivative of sine is negative cosine, but it was subtracted, so it's that evaluated pi over 2 to pi. Should we get the answer? We may as well. Let's just do it. Okay, first I plug in pi, 1/2 pi squared plus cosine pi minus, then I plug in pi over 2, so 1/2 pi over 2 squared plus cosine of pi over 2. This is going to be, let's see, 1/2 of pi squared, that's pi squared over 2. What is cosine of pi? -1. Minus, okay, be careful here. You're doing pi over 2 squared. Pi over 2 squared is pi squared over 4, but then times 1/2. So you should get pi squared over 8. And then cosine of pi over 2 should be 0. So we get here pi squared over 2 minus 1 minus pi squared over 8. We should probably get a common denominator of 8 between all of these. So I multiply top and bottom. Let's see, 4 pi squared over 8 minus 8 over 8 minus pi squared over 8. And then I just put all the numerators together, and that'll become 3 pi squared minus 8. Can't put those together unless we use a calculator and get a decimal. That would be the exact area. 3 pi squared minus 8 over 8. Questions?
It's funny. Looking at the numbers, I was expecting that one to be a lot harder than the previous one, but it was actually way easier.
Not too bad. All right, this one's tricky. I'm debating something right now. We'll do it next class. Okay. Make sure if you have your graphing calculators, bring them next class so I can show you something. All right. Because right now you need to know what these look like. And I have a feeling that you might feel a little uncomfortable with these. So I'm gonna teach you how to graph these on your calculators.
Isn't the second one going to be like a shifting of the square root one?
Yeah, this is a square root
funny
function that's been reflected and shifted.
Yeah.
This one is almost like a parabola.
Just a real skinny one.
It's really flat, close to zero. And then let me show you the picture. This is what we've got. Oh, wait, yeah. Make it a little smaller. There, just grab this. So I'm kind of cheating by just showing you the graph right now. Like I said, next class, I will show you how you could graph this. First of all, this one right here, x equals y to the 4th, that's this. Okay, it actually goes the other way too. It goes like this, like a sideways, almost like a parabola. But this restriction that y must be greater than or equal to 0 means we must be above the x-axis, which is why we're throwing that out. And then the blue one, this is the square root function, just looks weird. It actually continues this way like this. But again, because we're only going to look at y bigger than or equal to 0, we cut this off. So there's our region. Now, this is definitely best done with horizontal rectangles, because if you imagine moving those rectangles anywhere up and down in this region, you're always going to have the same function on the left and right the whole time, aren't you? Like it never changes. It's always the blue one on the right and the red one on the left. Whereas if you try to do these with vertical rectangles, it would switch right here. Not only that, look at both of these curves. They're both solved for x, aren't they? So they're already given to you as functions of y. So it's best for us to just treat this with a horizontal rectangle. So I need to do some integral going from c to d. I need to do the right one minus the left one. And I know it's going to be dy because I'm going horizontal, not vertical rectangles. The right one is what? The blue one. And the blue one is the square root one. So this is going to be integral
right
c
minus
to d,
left.
Right one minus left. The left one is y to the 4th. dy. All I have left are the limits of integration, which visually you can tell we start at 0 here, right?
Mm-hmm.
And then we're going to need to figure out where they hit each other, right? You can tell from the picture it's 1, but we'll do it ourselves. we're going to have to set these both equal to one another. Shit. Y to the fourth equals the square root of 2 minus y. That's how we're going to figure out this, right? Square both sides. And then we run into a problem. Because this, even if we move everything to one side, this is not a quadratic, right? So we have no simple way of solving this. There's not a simple way of solving that equation. So this problem, I think I took it out of the book. They are expecting that you can visually, from that equation, find the solution by inspection, that the answer is 1.
Okay, gotcha.
Okay, just they once you look at it and just be like, oh yeah, 1 works. Okay, which it does, right? So just be prepared for that, because that might happen in the homework where you're like, how do I solve that? And it's like, oh, there's the answer. You just have to think about it. So here's the integral that we're trying to set up and calculate right there. I'm going to stop here, but that will represent the area.
So sometimes we have to come up with the answer Plato style. We just got to think about it long enough.
Yeah, and usually it's an easy number. It's not some crazy number, you know. Let me see what my next example is. I think. Yeah, I like this one. Let's do this one. Sketch the region bounded by y equals the square root of x. I'm sorry, the square root, the absolute value of x, and y equals x squared minus 2. So I need a picture. All right, the absolute value of x, I'll do in red. Everyone here should know that that looks like a V. With a nice sharp corner there at the origin. And then x squared minus 2 is a parabola that opens up that's been moved down 2. So here's -2. So parabola opens up like this. It goes like that. And we want the area bounded by the 2, which is this area here. We're also going to need to know where these hit each other, right? And I'm going to be wanting to use vertical rectangles. Because no matter where I draw them, I've got red on top, blue on the bottom, right? So I want to do top minus bottom here. Where do they hit each other? Can you do it visually? Set them equal to each other. Can you do that visually?
Would it be 2?
2? 2 will work. How about -2? I think -2 works as well. Right? 2 and -2 both work.
You have to put it in like the summation where it's like for negative and positive, right?
What's that?
You have to put it in terms of like -x equals x squared minus 2 and positive x equals, like you have to put it in 2 separate because it's absolute.
Like if you truly wanted to solve this equation, you would have to set up 2 equations. One equation would be -x equals x squared minus 2, and then the other one would be x equals x squared minus 2. And then you solve each one of these. That's if you were going to try and do it algebraically. But visually, by just inspection, I can tell if I plug in 2, I'm going to get a solution and -2. So right now, as we sit, it looks like we could do this, right? Go from -2 to 2, do the top function minus the bottom function dx, right? Does it kind of look like this is following the format of what we've been doing, top minus bottom? What's wrong with this stuff? Or what's going to be a problem?
Would be the absolute value.
Yeah, what the hell's the antiderivative of the absolute value of x? We have not talked about that, right? We have not discussed that. So that's an issue. So because we're not sure what this is, we're going to approach it from a slightly different perspective. I want you to consider this. This graph is symmetric, meaning if I just look at this region, right, just the green, I can find the area of that and double it. And that would be the same answer, wouldn't it? So why don't we do this? Why don't we say we're going to double the integral that goes from just 0 to 2, right? But here's the key to doing it this way. If you ignore everything that's happening over here, can y'all tell me what the slope of that red line is right there? What's the slope of that line?
It's just 1.
Should be 1, right? Which means over here, this is just acting like the function x, not absolute value of x, but just x itself. So my top function can be x, not absolute value, then minus the bottom function, x squared minus 2 dx. I'm having such a hard time talking.
So I have a quick question. Since we dealt with this way, it does raise the question: is there a way to find? Is there an antiderivative for the absolute value of x, or is this just what you should do if you encounter that?
No, there is. It's just not. It's not a nice antiderivative. Here's. Let me get to that. Let's finish this up.
But there is a way. That's all.
Yeah, but it's easy. I can show it to you. But
Okay.
it's conditional, which makes it hard.
Ugh.
So this is equal to something, dot, dot, dot. I'm not going to do it. That's easy stuff, right? I think, yes. Just figure out what this is, double the answer, you're done. So in terms of the absolute value function, right? If we just go back to college algebra, what does the absolute value of x mean? Well, it means you actually have a piecewise function. It's x if x is greater than or equal to 0, and it's negative x if x is less than 0. In other words, if you go to draw this graph, what it's going to look like is this. As long as you're at 0 or to the right, which means if you're at 0 or over here on this side over here, drawing the graph, it's just going to be your identity function, which is just that, right? That's basically x. But if you're less than 0, it's going to be the identity, but going negative. So it's going to look like this. That's negative x, but you have to stop when you get to 0, right? That's the absolute value. So if you wanted to know what the antiderivative of this was, right, then it's going to be conditional. It's going to be the antiderivative of this, which is 1/2 x squared, as long as the x value is greater than or equal to 0. And it's going to be negative 1/2 x squared if x is less than 0. So it's like you take the antiderivative of this, as long as we're positive or 0 for x, and this if it's antiderivative of this if your x is negative. So there are two different possible antiderivatives depending on the value of x, which is why it was easier for us to just split it up and just look at the right side.
So thinking about that, I mean, in a situation like this, I would think it's probably always going to be better to split it in half.
From absolute values, most of the time.
You would hope that it's going to be symmetrical so you can do that.
Yeah, absolutely.
Because otherwise it's going to be awful.
Yeah.
Okay.
All right. I like to offer this as a bonus. And considering some of the grades on the last test, I would try it if I were you, just to see. let's say if you're interested in that as a bonus, you can email me the answer before the beginning of next class. And I do want you to take it all the way. So you're going to get some answer. It's probably going to be ugly, but.
Sir, what if it's like partially correct?
I'll just have to see what you have. Yeah. All right, we have 8 minutes. So let me do this, since we still do have 8 minutes, let me talk to you about your graphing calculators. So I wanted to be able to share my screen. But let's say, okay, on your graphing calculators, let's say you wanted to graph f of x equals sine x, right? Then on your calculator, you should have a thing where, now I'm assuming you have like a TI calculator. You should have somewhere where you go to type in the actual function, and it should say something like this, like y1 equals, and then you put in the graph, right? You type in sine x, right? And then you graph it and everything's good. Yes, everyone comfortable with that? Okay, what this really is us graphing y equals sine of x, right? That's what we're really graphing here. But what if I give it to you the other way around? What if I give you x is equal to sine of y? Unfortunately, on your calculator, there's no way to get it to say x equals. Okay, x equals, and then you type in something with y, right? Understand? So there is a way to do it though, all right? Here's what you do. We have to switch our calculator into a different mode. And so on your calculator, I'm not sure, depending on your calculator, there should be a mode button. And when you go to mode, under your graph feature, it should list several options. There should be function mode. It might say something like para, polar, sequence. Are y'all finding that? Those of you who are following along, y'all seeing that? Sorry, Hunter. The standard default that we use when we're graphing is function. What I would like for you to do is switch it over to parametric. Okay, so go to parametric, and then go back and go in like that's the call. Hold on. Okay, sorry about that. Okay, so you're in parametric mode, and then go back and do what you would do if you normally wanted to graph something. And when you go there, oops, I forgot to hit parametric mode. Oops. When you go there, it should now have something that looks like this. It's a very different looking. It says X T1 equals, and then Y T1 equals, and then X T2 equals, and then Y T2. Do you all see that? Those of you who are following along here? Here's what we're going to do. First thing, these things are grouped in twos, all right? So I want you to do this first. I want you to, instead, we're not going to use X anymore. We're going to use T as a variable. I want you to put here T, and then on the Y T1, I want you to put sine T. Okay? And then I want you to graph. And when you graph that, it's going to graph this. So I see at least one nod of their head, nod of the head, yes. That's your standard function. See, all you're doing, you know, like if you want to graph sine of X, you put sine X there, and you put sine T here, and you put T here for the X variable. Now what I want you to do is switch it. On the second one below it, I want you to put sine T for the X and T for the Y, and then graph again and watch what's going to happen. So we switch the X and the Y, and you should see this get graphed. Okay, so how does this work? Clear those out. I want you to graph these two things together. So Y equals X squared. Let's do that versus X equals Y squared. To do this in the parametric mode, your X T1 will be equal to T, and your Y T1 will be equal to T squared. Whereas here it'll be X T1 equals T squared, and Y T1 equals T. So they switch places. If you do that, you should get two pictures on one graph. One of them will be a parabola that opens up. That's this one. And the other one will be a parabola that opens sideways. I'll talk more about this next time. Bring your calculators. What I'm getting at is you can, using parametric mode, you can graph basically everything you've ever graphed before, but then you can also graph things that are not functions of X. You can graph things that are functions of Y. So that might help you if you're having trouble graphing something. Also, one more thing. I think on some of these, you're probably only getting half of the parabola if you graphed it. You have to go to Window and adjust your T minimum from -10, and then your T maximum to 10. I'll try and have my virtual graphing calculator on screen next time so I can show you the actual keystrokes and we can look at it together. I just don't have it installed on this computer right now. So, okay, homework tonight, do the 7.1. Okay, 1 through 19 odd. See how it goes. All right. Have a great day, everyone.
Thank you, sir. You have a great day too.
Bye.